All right, so we talk about simple monoalphabetic substitution, and we showed how it can be broken by frequency analysis. So actually, we can break every single letter substitution somehow because we have good computers. We can perform a lot of computation, so we can break it. So next step is to use digraphs, replace two letters with two letters. In history, this cipher used a lot, called Playfair Cipher, invented by Charles Wheatstone in 1854, a very old cipher. This is the first literal digraph substitution cipher. Use a 5x5 table containing a keyword and the rest of the alphabet. Memorizing the keyword and the 4 simple rules are enough to use Playfair. So this is the whole idea. But you may say that, okay, the inventor is Charles Wheatstone, but it is called Playfair because it was promoted by Lord Playfair. Because initially, British Foreign Office rejected this algorithm because of its perceived complexity. Wheatstone offered to demonstrate that 3 out of 4 boys in a nearby school could learn to use it in 15 minutes. But Undersecretary of the Foreign Office responded, that is very possible, but you could never teach it to attaches. Because actually the embassies will use this encryption algorithm, and they thought that it would be very hard for the officers to use it. But what happened is that British chose not to use it, but other countries started to use it, then British also started to use it. Okay. So let's look at an example. So assume that my plain text is cybersecurity again. I want to encrypt this. And as the keyword or the key, I use another word, cryptology. Okay. So as I said, first create a 5x5 table and write your keyword at the top of it. But now every letter has to appear once. So once I start to write cryptology, I don't write the second O here or the final Y here because I already wrote Y here, okay? So I write my keyword here, then I write the rest of the alphabet in the remaining order. The problem is that English alphabet has 26 letters, but here I have 25 places. But the letter J does not appear much in English, so this is why you put I and J at the same place. So when you decrypt back, the person who decrypts it back has to decide if the letter is I or J, depending on the context. But it is very easy to do it. So if you want to do it in Turkish, you might combine similar letters like C and Ç or O and Ö and that kind of stuff. Okay, so this is how you create it in English. Okay, so Ocha is my keyword. So this is my secret key now. This is actually called the key schedule algorithm, which we are going to see in block ciphers in the future. Okay, so I created this table. Now I need to know the rules to encrypt this plain text. Okay, the rules are as follows. If both letters are the same or only one letter is left, because since we are going to perform encryption on pairs of letters, if your word is, your plain text has odd number of letters, you have to add something more. In those scenarios, you add an extra X. Okay. So during the encryption, if the letters appear on the same row, by appearing the same row, so you are looking at this table. So if the letters you are going to encrypt are on the same row, you follow this rule. Replace them with the letters to their immediate right respectively. So if they are at the ends, you have to consider it as a cyclic, so you come back, okay? So here, wrapping around the left side of the row if a letter in the original pair was on the right side of the row. This is what it meant. So another option is if the letters appear on the same column of your table, replace them with the letters immediately below respectively. And if they are not on the same row and the same column, replace them with the letters on the same row respectively, but at the other pair of corners of the rectangle defined by the original pair. The order is important. The first letter of the encrypted pair is the one that lies on the same row as the first letter of the plain text pair. Okay, so rules are this. It is currently, it may not mean anything much to you, but now if we see it in an example, it will be very clear. So you write your plain text. I told you that this is a digraph encryption algorithm. So you partition them into pairs of letters. So at the end, cybersecurity ends here. So we have odd number of letters. I put an extra X as it is written in the first rule, right? Now I want to encrypt C and Y. So I look at my table. C is here, Y is here. So they're on the same row. The rule says that look at the first letter and replace it with one to its right. So you put R here, and for Y you put P here. Okay. Next, we are going to encrypt BE. So B is here, E is here. So they are not on the same row or on the same column. So consider them as the corners of a rectangle. So here you create another rectangle. I mean, the other corners become here. So you replace B with the one on the opposite side of it, and E with the opposite side of it, like here. Okay. Next one is R and S. Again, they are not on the same row or column. So these are now considered as the corners of a rectangle. So these becomes the other corners. So since I'm going to encrypt R first, I replace it with T. And when I encrypt S, I replace it with M. So instead of RS, if it were SR, it will be empty. So that is the idea. For EC, same thing applies. They are not again on the same row or column. For UR, again, you create a rectangle. For IT, now you are on the same column. So for I replace it with the one below it. For T, I replace it with one below it. So if I was going to encrypt Z, since there isn't anything below it, I would replace it with T. That is what I meant by wrapping it. Okay. And finally, YXR again creates a rectangle, and this is what you do. So the person who wants to decrypt it back, so they will have PW. Again, they will look at here. They create the same rectangle, and they obtain back YX. So this is used during the First World War, and it was broken a lot during the First World War. Okay. So why it is broken again, you can perform frequency analysis again. Without computers, it may take some time to count every pairs of letters, but by using a computer, this is very easy. But also, there are other weaknesses. For instance, if we go back to creating the key, as you can see, after the keyword, you write the alphabet in this order. So you can somehow guess what is going on here. And also, the rules are simple. So by looking at the ciphertext, it is not that hard to come back. Okay. So if the digraph doesn't work, like if we can break Playfair, what we can do to avoid this frequency analysis attacks? We can use polygraphic substitution. Instead of 2 letters, we can replace 3 or 4. But Playfair or digraph ciphers are still vulnerable to 2-letter frequency analysis. So computers allow frequency analysis on short polygraphic substitution, like Playfair. If you perform 8-character simple substitution systems, they are probably secure, but you cannot do it by hand, right? You have to create a table replacing every 8-letter with a different 8-letter. So even your key now will be maybe terabytes of data. I don't know. You have to calculate. So you cannot use it by pen and paper. But as you can see, key is too long for this kind of longer substitutions, and it is not easy to be used in practice. And encryption and decryption becomes too complicated now, right? Because if you have that kind of 8-character substitution, it will take a lot of time for you to find the correct 8-character and so on. So we cannot use it in practice. But the important thing is that this idea of polygraphic substitution leads us to the idea of block ciphers, because we will see that in the block ciphers, we will divide the input into blocks. And in modern days, we create the blocks as 64 bits or 128 bits. This means that 8 bytes or 16 bytes. Okay. So actually in block ciphers, we are replacing 8 bytes with 8 bytes. So it is not different than this kind of stuff. But of course, instead of letters, we are using bytes because now we are in the modern age. We have bits, right? We also want to encrypt things other than the letters, right? Because in computers, a byte might represent something other than a letter. Right? So this actually leads us to the idea of block ciphers. But if you look at historically, after this point on, pen and paper methods becomes easily broken. So now you want to create devices like Enigma and so on. And then we will move on to computer age and so on.